Welcome back. It's time to begin Chapter 3, and we will begin with a smattering of topics, with special emphasis on the second derivative of a function, which tells us something geometric about the graph of that function. This will bring us to the topic of concavity, and we will apply this stuff in the next video, which is about optimization, one of the major applications of differential calculus. Let's begin by thinking about the graph of some function f over some interval a through b. Here's a question. Based on this graph, is there anything we can say about the value of f prime of x that is true for all x in that interval a to b? So we're not looking for the value of f prime of x at some specific point. We're asking if there's something we can say about f prime of x for every x in that open interval. And after a minute or two of staring at the picture and thinking about what a derivative signifies, we should be able to answer this. Yes, there is something we can say about this function's derivative that holds for all values of x in that open interval. Namely, the value of the derivative will be positive for all x in that open interval. This holds because this function is increasing throughout this whole interval. As we move from a to b, the value of the function keeps getting larger, which means that in the infinitesimal neighborhood of any point on that graph, the graph just looks like a straight line with a positive slope. Now, at some places, the slope will be steeper than others. It looks like it's steeper over here than it is down here, for example. But since this function is increasing the whole way, the slope will always be positive, which means, of course, that the derivative will always be positive for every value of x in that interval. And similarly, if we were to look at a function that was decreasing over an interval, such as this function g, we should immediately be able to see that for all values of x in that interval, the derivative of g of x, g prime of x, will be negative. There shouldn't be anything mysterious about this. It's just that since the function is decreasing over this interval, if we were to look at the infinitesimal neighborhood of any point on the graph, we would see that the graph looks like a straight line with a negative slope. Maybe steeper at some places than at others, but negative at all, which of course we know means that the derivative of g would be negative at every point. Simple though these ideas are, let's summarize them down here. We have seen that if a function is increasing its value over an interval, as it was up here, then it necessarily follows that the function's derivative is positive over that interval, which we deduced up here. But we also saw, as in the second case, that if a function is decreasing its value over an interval, like our function g, then the function's derivative, as we saw up here, is going to be negative over that interval. Good. Quick observation, this arrow can be reversed as well. If we're told that some function's derivative is positive over some interval, that would mean that for all values of x in that interval, the function's graph locally looks like a straight line with positive slope no matter where we are. And consequently, even though we don't necessarily know what the graph of the function looks like, just the fact that its derivative is positive everywhere means that it has to be increasing in some way or other. And a similar statement could be made in the negative case. If I've got some function and I don't know what its graph looks like, but I know that its derivative is negative everywhere over some interval, that means at every point throughout the way, locally, the function is decreasing because it always looks like a straight line with a negative slope. Now again, it could be decreasing in all sorts of ways, but it will still be decreasing. So knowing that a function's derivative is negative over an interval is enough to tell us something about the function itself. It tells us that the function itself must be decreasing. And as a result, I can take this arrow and make it a double-headed arrow. Information about whether the function is increasing or decreasing over an interval tells us something about the function's derivative over the interval. But viewed the other way, information about a function's derivative, in particular whether it's positive or negative over an interval, tells us whether the function itself is increasing or decreasing over an interval. Now this connection here may be so obvious to you that it hardly seems worth our while to spell it out, but I want to do that as a first step towards a more subtle relationship between a function and its second derivative. To understand this one requires a little more careful thought. So let's go back up to our first function here. And I want to clean this up. Instead of having all this wordy stuff, I want to rewrite it as I wrote this one, now that we've got the basic point right here. So let's just say, in analogy with what we did down here, that for all x in that interval, we know that f prime of x, the derivative of this function, is positive. Okay, now I'll ask you another question. Is there anything we could say about the second derivative of x for all x in that interval? Well, all we have to go on is this graph. And at this point, we've said very little about second derivatives. We've talked about how in physical contexts, if the original function represents position, the second derivative can represent acceleration, but that doesn't really help us here, where we're just presented with a bare graph and we're asked to deduce something about the second derivative of the function. Let's see. Well, let's go to first principles. The second derivative of a function is itself just an ordinary derivative. It's the derivative of the derivative. And like any derivative, it represents a rate of change. But the second derivative of f represents the rate of change of the first derivative of f. The second derivative tells us the rate at which the first derivative is changing. And I understand how to think about the first derivative geometrically, so maybe thinking about that will help us. Well, let's see. So the second derivative tells us the rate at which the first derivative is changing. We know the first derivative is always positive here, but what about the rate at which it's changing? Well, let's see. The first derivative starts off fairly modest, and it's getting bigger and bigger and bigger as we go. Well, that's kind of interesting. That means that the value of the first derivative is itself increasing. Not just the function increasing, the first derivative is increasing. And if the first derivative is increasing over this interval, that means that its derivative, which is of course the second derivative of f, is positive over the interval. Aha! So f double prime of x itself is also positive for all x. Well, that was interesting. We were able to take this fairly obvious statement and deduce something from it that really wasn't obvious at all, that the second derivative of this function must be positive over this interval. And now you might think, well, this function was increasing, and we know that if a function is increasing over an interval, we know that the first derivative is going to be positive. But does that mean that the second derivative will also always be positive? It doesn't, because the fact that the function was increasing actually did not come into this deduction at all. Let me show you what I mean just by drawing another function on this same graph. Consider this function, h. What, if anything, can I say about h prime of x for all x in that interval? Well, that's not hard. H itself is an increasing function, so by our little implication here, we know that h prime of x must be positive for all values of x in that interval. But what, if anything, can I say about h double prime of x, the second derivative of h? Will it also be positive? Well, let's think our way carefully through this. The second derivative of h represents the rate at which the first derivative is changing. We know that that first derivative is always positive, but how is it changing as we move from a to b? Well, it starts out fairly steep, and as we move, that steepness, while remaining positive the whole way, gets less and less steep. Even though the value of the function is increasing, the value of its derivative is decreasing. That slope is coming down as we go. So if we're thinking about that first derivative, h prime, that's a function that's decreasing over an interval, and as a result, we know that its derivative, namely the second derivative of h, will be negative over the interval. So I can fill this in. H double prime of x will be negative for all x. So note well, f and h are both increasing functions, and therefore they both have positive first derivatives. But one of them has a positive second derivative, and the other has a negative second derivative throughout that interval. So just the fact that a function is increasing isn't enough to tell you anything about the sign of its second derivative. This is a more subtle relationship. Let's see if we can understand this idea down here. Given this graph of g, we've already said that for all x in the interval, g prime of x is going to be negative because the function is decreasing. Well, what about g double prime, the second derivative of g? Will that always be positive? Will that always be negative? Or some mixture of the two? Well, let's think about our graph and what the second derivative tells us. The second derivative of g is the rate at which the first derivative changes. Now, the first derivative is always negative, but as we move from a to b, what's happening to the value of the first derivative? It starts out a fairly steep negative, and it's rising up towards 0. So that means the value of the first derivative is increasing as we go from a to b. So the value of the first derivative is increasing over that interval, which means that that function's derivative, which is the second derivative of g, must be positive over the interval. So this second derivative has to be positive for all x in that interval. So even though the first derivative is negative for all x there, the second derivative is positive for all x there. And to drive this point home with one more example, let me draw on this same figure the graph of this function k. Now k is decreasing over this interval, which tells us immediately that k prime of x is going to be negative for all x in the interval. But of course my question here is, what about k double prime of x? What about the second derivative of k? Well, one last time, let's see if we can think our way through. The second derivative of k is the rate at which the first derivative of k is changing. We know the first derivative is always negative, but at what rate is it changing? Or what can we say about that rate? Well, it starts out negative, but not much below zero. But as we go, it's getting further and further below zero, which means that the value of k prime is decreasing. And as we've said, a function is decreasing over an interval. K prime will be decreasing over an interval if and only if that function's derivative, namely k prime prime, is negative over that interval. So that means k double prime of x is negative for all x in that open interval. And once again, notice that we saw the same thing down here that we did up here. Just knowing that a function is decreasing, as both g and k are, is not enough to tell you about the sign of the second derivative of that function. It could be positive, it could be negative. It's a more subtle relationship than the one regarding the first derivative. But can we capture this idea in an intuitive geometric manner? We can. Let's think about the two cases in which the second derivative was positive. That was f and g. And let's think about the graphs of f and g. In each of those cases, the graph of the original function was what we would call concave up, like a cup. The idea is that the graph of f over this interval looks a bit like part of a cup, this bit right here, whereas the graph of g over that interval looks like this part of the same cup. Any part of this cup, no matter how far you extend it, think of it as like a parabola, would be considered concave up. And that really is what is driving the fact that they both have positive second derivatives. Because if you think about this, if you think about like a upwards opening parabola, think about what its second derivative is like. Well, first of all, the first derivative is sometimes negative and then sometimes positive, because the function is sometimes decreasing and sometimes increasing, depending on which side of the vertex you're on. But the whole way, the value of the derivative is increasing. We go from steep negative towards a little less negative, a little less negative, creeping up towards zero, increasing until we get to zero. Slightly positive, still increasing, slightly more positive, very positive. It increases the whole way. Not the value of the function, but the value of its derivative. And now let me put these two cases aside and concentrate instead on the two cases where the second derivative was negative for functions h and k, this one and this one. Well, far from being concave up like a cup, those two are concave down like a frown. The graph of h looks like this part of the frown. The graph of k looks like this part of the frown. But they're both concave down. And it's the same story. If you think of, say, a downwards opening parabola, its derivative will be positive for a while, then it'll be zero, and then it'll be negative for a while, because it's increasing and then eventually it's decreasing. But its second derivative, for any concave down graph, is going to be negative the whole way, because that's giving us the rate at which the derivative itself is changing. Well, the derivative goes from very high values to lower and lower and lower and getting towards zero and then getting negative, but a small negative and a bigger negative and larger negative and huge negatives. So this cup is the typical picture of concave up. This frown is the typical picture of concave down. And if you spend a little time thinking about this and drawing pictures like these, you'll come to realize that this equivalency right here can be supplemented by a second one. A function's graph is concave up over an interval if and only if the function's second derivative is positive over the interval. And this is a 2-for-1 deal because we also have that a function's graph is concave down over an interval, like h or k, if and only if the function's second derivative is negative over the interval. So we can deduce some geometric information about a function's graph, where it's concave up or down, from the second derivative of that function, namely where it's positive or negative. I want to put these ideas to use a little bit, so I want to clear out the clutter here, box those up, and move them to a more convenient location. Okay, I decided that was the most convenient location after all. Now that we have our box of goodies here, let's talk about the contents of that box a little more. In the next video and section of the book, we will be discussing optimization, which is a major application of differential calculus. Roughly, the idea is that if we have some function, f, and we want to find the points where f's graph has local maxima, like these, or local minima, like these, we are looking for hilltops and valley bottoms. And the way you get to a hilltop is where your function is increasing for a while and then suddenly begins to decrease. And of course, the way you get to a valley bottom is where your function is decreasing for a while and then starts to increase. In both cases, these points, these local extrema as they're called, occur where the sign of the derivative changes, either from positive to negative or from negative to positive. And if we're looking for such places, well, of course, for the sign to change from positive to negative or negative to positive, it has to pass through 0. So the way we identify our prospective local extrema is to look for the places where the derivative of the function is 0. And this is something we can do analytically using what we know about derivatives. Much more on this next time, but I want to give you a quick example. Back in your precalculus days, you probably learned a method for graphing quadratic functions. It's a useful thing to learn in precalculus, not so much for its own sake, as for the techniques that are involved that you have to master in order to carry it out. Let me remind you quickly of how it works. Suppose we have a quadratic like this one, 3x squared minus 2x plus 1. The game in precalculus was to put this thing into a form in which you could recognize it as a stretched and shifted version of just plain old y equals x squared, whose graph everybody knows. And the first step was to complete the square. To carry that out, you need a leading coefficient of 1, so you have to factor a 3 out of this thing, like so. And we look at this expression inside the parentheses. Oh, how we wish it were a perfect square, but it is not. This constant of 1/3 at the end ruins everything. There's only one constant that can be added to the rest of this thing to make the whole thing a perfect square. And what is that magic constant? Hopefully you remember the way to get it. We take the linear coefficient, minus 2/3, cut it in half, which gives us minus 1/3, and square it, which gives us a 9th. And that is our magic constant. So we can say, if only this 1/3 were a 1/9. Wouldn't that be wonderful? Well, you can have what you want. You can just add a 1/9 in here, as long as you take it away as well. Like this. This equal sign holds because we've done no harm. Sure, we've injected a plus 1/9, but we've subtracted it as well. We have changed the form of this expression without actually changing its content. And now we have that perfect square we hoped for. In fact, if you stare at that for a moment, you will recognize that the stuff inside that box is the square of x minus 1/3. And of course, we still have this stuff which needs to be brought down, but I will simplify it first, giving us plus 2/9. Now I'll redistribute that 3 back through, giving us this expression. And this is much more appealing to our geometric intuition than the original form in which we had the quadratic, at least if you understand the basic geometry of stretches and shifts and the algebra that corresponds to those, because we can recognize this as just a distorted version of y equals x squared. Everybody knows that y equals x squared looks like this. It's the old U shape sitting on the origin. But this isn't y equals x squared. It's a twisted version of it. We start with this thing and substitute x minus 1/3 in for the x, getting a different function. And as you recall, substituting x minus 1/3 for x shifts this whole graph to the right by 1/3 of a unit, so that we would end up with something like this, where our U shape, which is in fact a parabola, has moved over to this point, 1/3 of a unit to the right of the origin. But this isn't what we were looking for. It's just part of the way there. To get from here to here, another thing we'll need to do is multiply this thing by 3, which would transform this equation into y equals 3 times x minus 1/3 squared. And you recall what multiplying a function by 3 does. It stretches the graph out vertically, so that the U shape would sharpen up here a little bit. Maybe something like this. I'm not going for exactitude here. So now we know what the graph of this thing looks like, and this is very close to what we were actually looking for, but we still have to add 2/3 on. So if we were to transform this one more time by adding on 2/3, we would get what we want. But what does that algebraic transformation do geometrically? Well, when you add a constant onto a function, it shifts the graph vertically. So this whole graph would move up by 2/3 of a unit so that it looked something like this. And the vertex of this parabola would be, therefore, at 1/3, 2/3. And that gives you the basic shape. Of course, you could find out where it crosses the y-axis pretty easily. In fact, that's clearly going to be at 1, so I'll put that on there too. But that's it. And if you carry this whole process out in a more general setting, you'll see that the same process always goes through, and you always get a stretched and shifted version of good old-fashioned y equals x squared. So in particular, you always end up with a parabola, because stretches and shifts preserve parabolas. Okay, that was your quick precalculus review. I should note also that unfortunately sometimes in precalculus, what people learn is a formula for how to find the vertex. Now that does greatly shorten this somewhat tedious process, but it's a counterproductive thing to really be using in precalculus, because what's important in this lesson is not actually graphing quadratics. As you'll see, that's a trivial process once you know a little calculus. What's important in this precalculus business is all these various techniques you use. Completing the square, thinking about the connections between algebraic transformations and geometric transformations. It's very good for that. But if you just memorize a formula, then you miss all the good stuff that can be used in lots of other places, and you just have something else in your head that nobody really needs. Anyway, I promised you this is very easy once you know a little bit of differential calculus, and you do know a little bit of differential calculus. So let's redo this problem of graphing this quadratic with some help from calculus. We know from our precalculus days that this is going to be some parabola. The only question is which one? What is it going to look like? Well, we also know from our precalculus days that it is either going to be one that opens up like this, or one that opens down like that. Either way, it is going to be distinguished by a vertex at which the tangent line is horizontal. In other words, where the derivative of the function is 0, because that's where the function changes from increasing to decreasing, meaning the function's derivative changes from positive to negative, and therefore must be 0. Or the other way around, it changes from decreasing to increasing, which is where the function's derivative changes from negative to positive. And for it to make that change, it has to pass through 0. So, the parabola's vertex will occur where f prime x equals 0. In other words, where, well, what is f prime of x? F prime of x is 6x minus 2. So we're looking for where that is equal to 0. And this happens when x equals 1/3, of course. Aha! And now we've got the x-coordinate of the vertex. No need for some dopey memorized formula, and no need for the algebraic tortures of completing the square. No need even for all those geometric transformations. This reasoning should be crystal clear. Even the algebra involved is trivial. It's solving a linear equation. Anyway, this is enough to get us started on the graph. We know the vertex will have an x-coordinate of 1/3, so it'll lie somewhere on that line, but where on that line? Well, the vertex's y-coordinate is easy to find. We know its x-coordinate, so all we have to do is pop that into the equation. The y-coordinate will be f of 1/3. And if you run 1/3 through that, you end up with 2/3, just as we found with our precalculus methods. So I can go ahead and put the vertex on my graph, and there it is, at 1/3, 2/3. Well, what does the rest of the graph look like? It's a parabola, and this is its vertex, so it either opens up or it opens down. Well, there are different ways to see what it's going to do, but the easiest is just to find another point on the parabola. Let's find where it crosses the y-axis. Well, it crosses the y-axis where x is equal to 0. And if x is equal to 0, then f gives us 1, which means that our parabola crosses through here at 0, 1. And since this is the vertex and it passes through this point, symmetry tells us that it'll pass through a point right here. And ultimately, our parabola will look something like this, which is, of course, what we found last time. This is our graph of the quadratic function f. Wasn't that easy? As you can see, there's no need to memorize anything about the vertex, since it takes 2 seconds to set the derivative of a quadratic to 0, and you don't have to go through all of that precalculus stuff either. And this all came down to finding the place where the derivative of this thing is 0. That's what we're going to be using again and again and again when we get to optimization very soon. But before we get there, I want to say a few things about this second part of the boxed result down here that has to do with the concavity of a graph and the relationship to the second derivative. Oh, actually, before I erase all this stuff, let's relate the second derivative stuff to it. What's the second derivative of this function? Well, the first derivative was 6x minus 2. That means the second derivative is the constant function 6. That means that the function's second derivative is always positive over all real numbers. That means that the graph should be concave up everywhere. And indeed, it is. So, just a bit of confirmation. Okay, if we have the graph of a function, like so, we could, as we just discussed, find local maxima and local minima by setting the derivative equal to 0. But some other points that often are important in describing a graph are the so-called inflection points of a graph. These are where the graph changes the direction of its concavity, shifting from concave up to concave down, or concave down to concave up. On this graph, for example, we can see that there's an inflection point somewhere around here. Prior to that point, at least for a little while, the graph was concave up, like a cup. After that point, at least for a while, the graph is concave down, like a frown. So this would be an example of an inflection point. It's not the only one on this graph, but it's one of them. Here are some other inflection points. And since inflection points are where the graph changes its concavity, this result down here gives us an easy way for locating potential inflection points. Where the graph is concave up, there the second derivative is positive. Where the graph is concave down, there the second derivative is negative. So if it's going to change from concave up to concave down, then the second derivative is going to have to change from positive to negative, or maybe from negative to positive, as the case may be. Either way, for this second derivative to change its sign, it has to pass through 0. Which means that if we want to look for inflection points analytically, what we want to do is look at the second derivative of a function and see where that second derivative is 0. And just as second-degree polynomials all have one place where the first derivative is equal to 0, corresponding to the vertex of the parabola, third-degree polynomials, whose graphs look something like this, or sometimes they have bumps in them, and of course they can go the opposite directions as well, like that. Third-degree polynomials have these graphs like that, graphs of cubics, and all of them are marked by a single inflection point, which can easily be found by setting the cubic's second derivative to 0. And the second derivative of a cubic is a linear function, so that's easy. Anyway, for those of you who are interested, I have a long, multi-part, and I hope intriguing homework problem in the textbook about cubics, which actually relates them to the history of complex numbers. So if you want to know something about where that mysterious number I, the square root of -1, comes from, you will want to do that one. And in the next section, when we discuss optimization, we will be using this business about the second derivative as one means of distinguishing local maxima from local minima. Because if you have identified a point where you have a local extremum, like here or here, but you can't see the graph, you just know that the first derivative is 0, how can you tell whether you are at the bottom of a valley or the top of a hill? How can you tell purely analytically without looking at a graph? Well, you can see what the second derivative looks like there. If you're at the bottom of a hill, then you are in a concave up situation, and you'll be able to identify that by seeing that the second derivative is positive, because that corresponds to concave up. If you are at the top of a hill, then you are in a concave down situation, and concave down corresponds to a negative second derivative. So by checking the second derivative there, you can find something out about that. But anyway, we'll see that next time. For now, I just wanted to make these important connections. But there is one last thing I need to do in this video, which is to introduce some notation, namely Leibniz notation for second derivatives and higher order derivatives than that. We know that if y equals f of x, we can express the derivative of this function in prime notation as y prime or f prime of x, and in Leibniz notation as dy dx. And in prime notation, the second derivative is obvious. It would be y double prime or f double prime of x. But what would it look like in Leibniz notation? Well, it's ugly. Instead of something nice like f double prime of x or y double prime, to express the second derivative of y with respect to x in Leibniz notation, we write this horrible thing. I am ordinarily an enthusiastic advocate for Leibniz notation, but I must admit the notation for higher order derivatives is pretty ugly. And it doesn't have the advantages that Leibniz notation has for first derivatives. dy dx is great because it's a ratio of infinitesimals. These two things don't mean anything on their own. This is not a ratio of anything. This whole symbol has to be read as just one thing that can't be separated out. Where did this ugly expression come from? Well, the idea is that you start with the first derivative, dy dx, and take the derivative of that. So far, so good. And then the crude idea is that, well, you've got two d's upstairs, so that kind of looks like a d squared y, so you put that like that. Now again, this is not actual algebra here. This is just explaining where this ugly notation comes from. And you've got two copies of dx here, so we can write it like that. And again, we are not multiplying these things. This is applying the derivative operator to this function. Anyway, don't blame me. I didn't make it up. I'm not even sure Leibniz himself created this, and it's hard to think of a good alternative. Fortunately, we usually end up using prime notation for higher order derivatives. And this does, by the way, extend, as you might expect, since this thing represents the second derivative of y with respect to x. If we turn those 2's into any other number, we get that derivative. So for example, this stuff represents the third derivative of y with respect to x. And the same would hold for the fourth, fifth, sixth, seventh, and so on. So let's look at a quick example. If y equals sine of x squared, find the second derivative of y with respect to x. And again, you have to write these things out on your own just so you get used to this weird notation. There's nothing difficult about it, it just takes getting used to. Anyway, let's get to our solution. If y is sine of x squared and we want the second derivative, well, we're going to have to go through the first derivative first. So let's take it. This, of course, is a job for the chain rule, since this is a composition of functions. We take the derivative of the outer, which gives us cosine, evaluate at the inner, so that we have cosine of x squared, and multiply by the derivative of the inner, which gives us another factor of 2x. So we have our first derivative. Well, the second derivative is just the derivative of the first derivative. Thus, the second derivative of y with respect to x is the derivative, there's that derivative operator, of the first derivative, which we just found. And this, of course, is a purely mechanical procedure. It's going to involve both the product rule and, inside the product rule, the chain rule. I guess I'll carry it out here for practice. The product rule tells me this is going to be the first factor's derivative times the second factor. The first factor's derivative is 2, so that's going to be 2 cosine x squared, but that is just one of two terms. The second term is going to be the first factor times the derivative of the second factor. In other words, 2x times the derivative of cosine of x squared. And we still have to take this derivative, which will involve the chain rule. So we will have 2 cosine x squared, just bringing that up, plus 2x, bringing that up. And now the chain rule here is going to give me the derivative of the outer, which is minus sine, evaluated at the inner, x squared, times the derivative of the inner, which is 2x. All this junk can be simplified to minus 4x squared sine of x squared. And that's that. Now you know the nasty Leibniz notation for higher order derivatives. I guess there is one last thing I should say about prime notation for higher order derivatives. If we have a function f of x, its first derivative is f prime of x, and its second derivative is f double prime of x, and its third derivative is f triple prime of x. But I think you can see the problem. Suppose you have reason to refer to, say, the 10th derivative of f. You obviously don't want to write this, because no one can tell at a glance how many primes are there, and God forbid you ever need to talk about the 100th derivative of f. Well, the convention in this case is that instead of using primes, we just write the order of the derivative in parentheses in that position. So we would rewrite this as this. That expression right there corresponds to the 10th derivative of f. We won't need anything even remotely approaching derivatives of such high order until we get to Taylor series in the 7th chapter of the book, which is a good way off since we are just beginning the 3rd chapter. But you should know the notation.